In this video lesson, we're going to look at counting theory and permutations. We're going to make sure you know how to apply the fundamental principle of counting, and we're also going to answer permutation problems that use the multiplication method. Let's look at a typical problem where we are ordering a car and these are our options. We could have a sedan or a hatchback. Both of those come in 5 colors, and they both come in 3 models, GL, SS, or SL. Now, oftentimes we've approached these problems by making a tree diagram. So here's our tree diagram. We start with the sedan or hatchback. Either one could come in the 5 colors. We so far have 10 options. After we add the 3 models, we have a whole lot more options. We could count them all across, or we could simply multiply. We have 2 options for the body, 5 options for the color, 3 options for the models, for a total of 30 options. This can be summarized with what's known as the fundamental principle of counting, which talks about if our events are independent. So let's just go back. The body style is independent from the color, is independent from the models, because all 5 colors and all 3 models show up in both body styles. So those are independent events. And so if that's the case, what this says is if we know how many ways for event 1 and event 2, and in our case we had event 3, all we have to do is multiply the options. All right, so let's take a look at this problem. A restaurant offers a choice of 3 salads, 4 main dishes, and 6 desserts. How many different 3-course meals consisting of 1 salad, 1 main, and 1 dessert are possible? Well, we don't have to make a tree diagram because we know the fundamental principle of counting, and we simply can multiply 3 times 4 times 6 to get a total of 72 different meals. No wonder it takes people so long to make their options or choices sometimes when ordering. All right, let's go to a different kind of problem. Let's say we're making a code. Let's say it's a passcode to get into somewhere. And it has to consist of 4 letters and they can repeat. How many codes are possible? So what I like to do is just create blanks for each of these to see what my options are. And notice I've got a time sign there because I know I'm going to multiply them. Well, there are 26 letters in the alphabet, so I have 26 options here, and 26 options here, and 26 options here, and also 26 options there. And now I'm probably going to need a calculator to figure out this answer. And I get an answer of 456,976. So it shows you that if you're just trying to guess someone's code, that would not be an easy thing to do. Now let's take a look at what's the difference if the letters cannot repeat. So we still have 4 letters, and we're told that, let's see, I have 26 options here, but then I can't repeat that letter. So now I only have 25 options left. Since I've used up 2 letters, I only have 24 options, and here I have 23 options. And so now I can multiply those, and I get a few fewer, but still quite a few options. There are 358,800 options if I don't allow repeats. All right, so let's see, what if it's a code of 4 numbers? Well, if I take my digits 0 through 9, there's actually 10 digits I can choose from. So, and if I allow repeats, then I'm going to have 10 times 10 times 10 times 10. That's a lot easier to multiply in my head. That's just 10 to the 4th, which of course is a 1 with 4 zeros, or 10,000 options. Not nearly as many as with the letters. And if I have no repeats, on the first spot I had 10 options, but in the next I had 9, then 8, and then 7, and I can multiply those out for a total of 5,040. So we go down significantly when we're just using numbers with no repeats. But you can think of your garage door. Maybe it has a 4-digit code. How many different options are there? How secure do you feel? All right, let's take a look at if I had the letters in Irondale. So how many ways can I arrange the letters in Irondale? So let's see, I've got 8 letters, and they're all different. And so in the first spot, I'd have 8 choices, and the next 7, and the next 6. And I'm going to be doing all of those, 5, and then 4, and then 3, and then 2, and then the last spot I only have 1 letter left, which is the same as 8 factorial. And if we do 8 and we want to do factorial, we go under the math menu and over to probability. You'll see that it is choice 4. And 8 factorial is 40,320 options. Now let's say we're only interested in 4 letters. So a 4-letter code, well, we start it with 8 options, and then 7, then 6, and then 5. And so we get a total of, oops, entering my numbers in wrong, here we go, 1,680. These problems, by the way, are known as permutations. So permutations are where we are arranging elements, no repeats, and order matters. No repeats, and order matters. All right, let's take a look at our next problem. Let's say you saw a license plate and you remembered it started with the number 5 and ended with the letter Z. For some reason that's stuck in your mind, but boy, you just can't remember anything else except that it was 3 numbers followed by 3 letters. And you also remember none of them repeated. So let's see how many different license plates could meet that requirement. So here we go. Um, We've got our 3 numbers. So we knew this started with a 5, so there's only one option there. I'm not actually going to write the number 5 there because really I'm looking for the number of options. I knew this was a 5, so there's one option there. And I knew this was a Z, so there's only one option there. So 5 and a Z. Now, we know it's 3 numbers, and we know that nothing repeats. So that's either 10 numbers in all. I used up the 5. That means I have 9 options left here. And then since I don't repeat again, I only have 8 options left here. So remember, 10 numbers. I used the 5 up, so now I'm down to 9 numbers here. I use a letter here. Now I'm down to 8. All right, let's do the same thing over on here. We have 26 letters, but we already used the Z, so I'm down to 25 letters. So I have 25 options here. After I use a letter there, I'm down to 24 options because I have no repeats. And we will see that the number of different license plates that are possible that meet that requirement are 43,200. All right, let's try this problem. So let's say I'm on a volleyball court. Actually, this is true. On a volleyball court, the starting positions are numbered 1 through 6. It actually starts with who is serving. So 1, 2, 3, 4, 5, and 6. So they rotate around the court like that. So let's say a team had only 6 players show up. How many ways could the coach place them to start the game? Well, we've got 6 positions, right? And we have 6 players. So we start off, well, we have 6 options for position 1. Now we're down to 5 for the next, and we can just put them all in order going down. In the last spot, we've only got 1 person left, and we get 6 factorial. Again, to figure out 6 factorial in your calculator, you hit Math, go over to PRB, and it's your 4th choice. And 6 factorial means there are actually 720 options for how that coach can arrange them on the court. Now let's say actually everyone showed up and there's 9 players on the team. Now how many ways can the coach put them on the court to start the game? Well, we still have 6 positions. But the first one, we have 9 options, then 8, 7, 6, 5, and 4. And we can just multiply those out. 9 times 8 times 7 times 6 times 5 times 4, for a total of 60,480 options. All right, so here's our last problem. We're going to look at how many different 7-digit telephone numbers can be made where the digits alternate between even and odd and no numbers repeat. All right, so I'm going to just put my even numbers over here. So 0, 2, 4, 6, 8, and then I'll have a list of odd numbers, 1, 3, 5, 7, 9. I can see I have 5 of each. Now, it didn't tell me what the first one had to be. So I actually have 10 options here. Now, depending on whether it was even or odd, I got to figure out how many options I have here. So let's say the first number was even, and I took out one of the even numbers. The next number is odd, so I actually have 5 options. Now let's say I had started with an odd. The next number would be even, so I'd have 5 options. All right, so it really doesn't seem to make a difference. So let's see that we have 5 options here. Okay, so now I took out one of these, and I can see that I'm going to have 4 options, whether I'm going even or odd. All right, so let's just keep going and say it was this way. So oh, I got to keep track of what I was doing. So let's go back and let's just assume that we started with an even here. Okay, so then we had 5 options for an odd here, right? And we know it makes no difference which one it was. So it'll alternate either way. So I have 5 options for an odd. I picked an odd number. Now I have 4 options for an even number. So we'll just go even here. And then we're going to just go back and forth, even, odd, and even. So let's see. I used an even. I had 4 options. I crossed that one out. And now over here, I have 4 options for my odd. Cross out one of those. And now I have 3 options for the next even one. Cross out one of those. And now I have, let's see, 3 options for an odd. Cross out one of those. And last, I have 2 options for an even. And there we go. We used up 7 numbers, and we can just multiply those then. 10 times 5 times 4 times 4 times 3 times 3 times 2, and we get 14,400 different phone numbers that have that happen. Now you might be bothered that I started with even here, but it doesn't change anything if I'd started with odd. Oops, I don't want to get rid of that answer. Let's just, if I started with odd here, I'd just have even, and the numbers would all come out the same. Remember, I allowed for all 10 options in the beginning, and how I crossed out, since both lists had 5, really make no difference. All right, so I think you're ready for your homework now, and it's in section 8.4, 35 through 43, and 47 through 50.